Good day. So let's have another example for the selection of section for a flexural member here in steel design. Okay, so using 345 megapascal steel and LRFD method, select the lightest available section for the beam loaded as shown. So bracing is provided only at ends and at midspan. So this is our beams loaded as shown. So we have concentrated loads at the midspan, and dead loads and live loads, uniform dead loads and live loads, including the self-weight. So according to the problems, we have bracing are provided at ends and at the midspan. So therefore, we can tell that the unbraced length is equal to 4.3 meters, or that is equal to 4,300 millimeters. So let us compute for the ultimate load for the concentrated loads. So this is, we have a piece of U is equal to 1.2 of the dead load plus 1.6 of the live load. So we have our piece of U is equal to 1.2 of 26.7 plus the 1.6 of 35.6. So this is our piece of U is now equal to 1.2 of 26.7 kilonewtons plus 1.6 of 35.6. That is equal to 89 kilonewtons. Then next, we have this two uniform loads. So we have for the ultimate uniform load, that is equal to 1.2 of the dead load plus 1.6 of the live load. So we have ultimate uniform load is equal to, this is 1.2 according to this problem, including self-weight of the beam is 14.6. And then plus we have 1.6 of the live load is equal to 25.5. So the ultimate uniform load is now equal to, so we have that as the 14.6 of the dead load plus 1.6 of live load, 25.5. So we have it as 58.32 kilonewtons per meter. Now computing for the ultimate moment based on this loadings, our M sub U, since we have a concentrated load and it is at the midspan, the equivalent moment, it will be equal to P sub U times L. This is divided by 4. The concentrated load at the midspan. Then for a uniformly distributed load, the maximum moment is the M sub, or is the W sub U. The ultimate uniform load times the length squared. This is divided by 8. Then computing for our M sub U is equal to, this is 89 kilonewtons. The total span of our beam, our total span will be equal to, so 4.3 plus 4.3 is obviously equal to 8.6 meters. So this is equal to 89 kilonewtons multiplied by the total length of the beam is 8.6, to be divided by 4. Then our uniform load is equal to 58.32. Then the length is 8.6 squared, then divided by 8. So this will be the ultimate moment based on our loadings. So you have 89 multiplied by 8.6 over 4. And then plus, we have that as 58.32. The total span is 8.6 squared, then divided by 8. So we can have it as 730.52 kilonewton meter. So this is our ultimate load based on our loadings. Now how do we decide which section will be used? So let us first assume that our section or our beam will be under zone 1, but we need to check this one later. If it is under zone 1, so we can have the value of our M sub U equal to, that is the reduction factor for bending P, multiplied by the M sub N, or basically equal to, This is f sub y, or that is our reduction factor p, multiplied by the fy, then the plastic section modulus with respect to x. So we need this value of our section modulus, just a reference value based on this computed ultimate moment. So let us compute. Then this is equal to 730.52, then to be multiplied by 1000 squared, to be in Newton, millimeter, is equal to reduction factor for bending is 0.90. Our Fy is 345 megapascals. Then what will be our required plastic section modulus? Again, this value is just our reference. Then later on, again, we need to check if it is really under zone 1, under zone 2, or under zone 3. So let us compute for this reference value. 730.52, this is times 10 raised to 6. And then to be divided by 0.9 by 345. Then let's say divided by 1000. That is 2352.72. And this is 2352.72. This is times 10 raised to 3 millimeters raised to 3. So this will be our reference value for our the plastic zone. That is the modulus of plastic section modulus. Sorry. So this will be our reference value. Then we need to check for a section, or we need to look for a section with a value of plastic section modulus greater than 2352.72. So we go on our database. So we are going to check the value of the section modulus in millimeters. Here. So we go to the 2000. So 2352. 2352, then I think we can use this one. So we have a section modulus of 2360. Okay, for the section W21 by 62. So we may, let's say, we may try W21 by 62. Okay, so this will be our trial section. Okay, so we just list down the properties of W21 by 62. So next step is that we need to check if it is really under zone 1. So let's have, again, our unbraced length, that is the L sub B, is equal to 4.3 meters or 4,300 millimeters. So we need to compare that value to the value of L sub B equal to 1.76 of the R sub Y multiplied by, that is the modulus of elasticity, divided by the value of F sub Y. Okay, so let us compute for the value of L sub P. L sub P is equal to 1.76 of Ry, that is 45 millimeters, and square root of 200,000 megapascals, and our Fy is equal to 345. So the value of L sub P is equal to 1.76 of 45, then the square root of 200,000, then to be divided by 345. That is equal to 1,906.91. 1,906.91 millimeters. So this is obviously less than our unbraced length, which is equal to 4,300 mm. So therefore, our section will may fall on zone 2 or zone 3. So it depends on the value of our L sub R. So let us compute for the value of the L sub R. So from our reference, so we will be using this equation, or the equivalent of L sub R. Okay, so we'll be needing the value of the R sub Ts. Okay, the R sub Ts squared is equal to the square root of the moment of inertia with respect to y axis, then the warping constant C sub W, then to be divided by the section modulus with respect to x axis. That is the elastic section modulus. So from the properties of W21 by 62, R sub Ts squared is equal to the square root of, what is the value of our I sub y? 23.9, this is times 10 raised to 6. Okay, the warping constant is 1,600 times 10 raised to 9. Then to be divided by, the section modulus is 2080, or the elastic section modulus. So computing for the effective radius of gyration is now equal to, this is the square root of 23.9, this is times 10 raised to 6, multiplied by 1,600, this is times 10 raised to 9, then to be divided by 2080 times 10 raised to 3. Then we take the square root. That is 54. We can have it as 54.53 millimeters. Okay, then for the value of our C, for this equation, for symmetrical I shape, the value of C is 1.0, and the value of the H sub O is the D minus the thickness of the flange. So we have, what is the total depth of this section? 533, then the thickness of the flange is 15.6. So we'll be using these two values. Okay, the value of D and the thickness of the flange. Okay, so our H sub O is equal to 533 less 15.6. Okay, we have H sub O is now equal to we have it as 517.4 mm. So I guess we are now ready to substitute our values to this equation. So let's have the equivalent of the value of the L sub R. L sub R is equal to 1.95. Our R sub Ts is 54.53. Then to be multiplied by the modulus of elasticity is 200,000 megapascals. Then divided by 0.7 of 345. And then to be multiplied by the square root of J. Okay, the value of J is equal to, we have 762, this is times 10 raised to 3, then multiplied by C, which is 1.0. And then divided by S of X is 2080, this is times 10 raised to, times 10 raised to 3. Then multiplied by the H sub O, 517.4. Okay, then to be multiplied by, this is the square root of 1 plus the square root of 1 plus, this is 6.76. Then to be multiplied by 0.7 of Fy, that is 345 megapascals. S sub X is 2080, this is times 10 raised to 3. Then H sub O is 517.4. Then all over, the modulus of elasticity is 200,000 megapascals. Then the value of j is 762. And this is times 10 raised to 3. Then the value of c is 1.0. So this quantity is squared. Okay. So again, I will be starting computing for this value of r. We'll be starting on this term. Okay, on this close bracket. Close bracket squared. Okay, this is 0.7 of 345. Okay, then 2080. This is times 10 raised to 3. Then 517.4. Then to be divided by 200,000. Then 762. Okay, this quantity will be squared. Okay, then multiplied by 6.76. Okay, then plus 1. Okay, and then square root. Okay, then plus 1 again. And then square root again. And then we are to multiply this value to the, this is the square root of 762 times 10 raised to 3. Then to be divided by 2080 times 10 raised to 3. Then multiplied by 8 sub o, 517.4. Okay, then we multiply the value to the ratio of, let's say, answer multiplied by 200,000, then to be divided by 0.7 of 345. Okay, then multiplied by 54.53, then 1.95. Okay, that is 5,517.99. So let's say we have our L sub r is equal to 5,000. This is 5,517.99 millimeters. So 5517.99 millimeters. So obviously, based on our previous values, this value of L sub r is obviously greater than our L sub b equal to 4,300 mm. And L sub b is greater than our L sub p equal to 1,906.91. So our section will fall under zone 2. Okay, so it will be zone 2. So if it is zone 2, then we need to compute the value of the C sub b. Since for this problem, we don't have the value of the C sub b. Okay, if you go back on our problem, we don't have the value of C sub b, or C sub b is not given. So our next step now is we need to compute for the value of C sub b. So since the value of C sub b is not given, so we need to compute for its value. So design of beams, zone 2. So bending coefficients, Mmax is the largest moment in an unbraced segment of a beam. MA, MB, and MC are respectively the moment at the 1/4, 1/2, and 3/4 point in the segment. So we go back to our beam. So we need to divide this 4.3 meters into 4. Since we need 1/4, 1/2, and 3/4 point of this unbraced length. But before that, so we may first do our shear and moment diagram. Okay, so for us to do our shear and moment diagram, first we need to compute for the support reaction or support reaction. Since we have a uniform loading, basically we have now our ultimate load, concentrated load, that is the piece of U, and the ultimate uniform load. So we have equal support reaction since this concentrated load is at the midspan. So let's say our support reactions will be R. So by summation of forces, this is summation of forces vertical equal to 0, assuming upward forces to be positive. We have 2R, then minus our piece of U is 89, minus 58.32, the total span is 8.6 meters equal to 0. So we have the support reaction is now equal to, this is 89 plus 58.32 multiplied by the total length. We have 8.6. And then to be divided by 2. So let's say our support reaction is equal to 295.276. So 296 kilo newtons. If we are to draw our shear diagram, so we have now the value of our R is equal to 295.276. So from 0, so we go up to a level or to a magnitude of 295. Let's say this is 295.276. Since we have a uniform loading, okay, so for this uniform loading, that is our W sub U. Okay, again, this is the 58.32 kilonewtons per meter. And our P sub U is equal to 89 kilonewtons. Okay, so this is, our loading here is a 0 degree load. So our next diagram should be first degree. So that will be 295.276. Okay, that's 200. We have 295.276 less 58.32. That is our uniform load. Okay, that's our uniform load. Okay, multiplied by the span, which is equal to 4.3 meters. And that is equal to 44.5 kilonewtons. So our diagram should be so from 0 to 295.276. So less that uniform load. This is first degree. This is equal to 44.5. Is that 44.5? Yes, 44.5 kilonewtons. Then 44.5 kilonewtons less that downward ultimate concentrated load 89. Minus 89, and that will give us negative 44.5. This is negative 44.5. Then negative 44.5 less, this again 58.32 multiplied by this span, 4.3. So minus the 58.32 multiplied by 4.3 meters. And that will give us negative 295.76. This is negative 295.276. So again, we have equal reaction, which is equal to 295.276. So that will give us 0. So this is our shear diagram. So again, our shear diagram should be first degree. Now we are to proceed to our moment diagram. Okay, so for our moment diagram, so our focus is how to determine the values of the moments at the quarter points for an unbraced length of 4.3 meters. So we are dividing our unbraced length, that is the L sub B divided by 4, for the quarter points. So we have 4.3 divided by 4. And this is equal to 4.3 then divided by 4. So it should be at 1.075 meters. So we are to divide our unbraced length at every 1.075 meters. Then we need to determine the value of the moments at each point. Okay, so our unbraced length is 4.3 meters, then divided by 4 is, we have 1.075. So how do we determine the moment at each point? So let's say, so at this point, we need the value of the moment. Let's say this is the moment at A. At 1/2, this is the moment at B. Then we have at C, let's say this is the moment at C. So we already know what is the value of our M max. The value of our M max is, this is our MU, equal to the 730.52 kilonewton meter. So all we have to do is determine the value of the MA, MB, then MC. So again, so our beam or this unbraced length is divided at every 1.075 meters. So let's say this is 1.075, 1.075, and 1.075 meters. So how do we determine the moment about that point? So all we have to do is maybe for an easier computation, all we have to do is write our moment equation. We cut this beam on this section, and we assume that a distance will be at a distance x from the left end. So what will be that moment equation? So our moment equation will be that moment at a distance x is equal to the support reaction, that is 295.276 times the distance x, then minus what is our uniformly distributed load. Again, our uniformly distributed load, the W sub U, is the 58.32 kilonewtons per meter. So all we have to do is subtract that on the right side of our equation. That is 58.32 times the distance x. Its lever arm will be at a distance x over 2. Then the moment at a distance x will be equal to this. This will be our simplified moment equation. M sub x is equal to 295.276 times x minus what is 58.32 then divided by 2. And that will be equal to 29.16 multiplied by x squared. Okay, so we are now ready to compute for the moment at A, moment at B, and the moment at C. So we have at x is equal to 1.075, we can compute for the moment at A. So this is, we have moment at A is equal to 295.276 times x, or that is ay 1.075 minus, we have the 29.16, then multiplied by ay 1.075 squared. So this will be the magnitude of the moment at A. So we have 295.276, then alpha x. I'll be using the calc function of calculator. Minus 21.16 alpha x squared. Then I'll be just pressing calc at x is equal to 1.075, then press equals. That is 283. We have 283.72 kilonewton meter. Okay, that is the moment at A. Then next is the moment at B. So the moment at B, that is at a distance, twice of 1.075. So what is that value? 1.075 times 2 is 2.15. Okay, so 2.15 meters. Okay, we can compute for the moment at B. So from our functions, all we have to do is press calc. Okay, the value of x will be at a distance, 2.15 meters. That is 500.05. Okay, we have the moment at B is equal to 500.05 kilonewton meter. Okay, so we have now the moment at A and the moment at B. So what about for the value of the moment at C? Okay, the moment at C is at a distance, x is equal to 3 times 1.075, and this is equal to 3 times 1.075 is equal to, that is at x equal to 3.225 meters. So at that point, we have that as the moment at C. So the moment at C is now equal to, so again, from our calc function, so we have the value of x as 3.225 meters. And that is equal to, we have that as 648.98 kilonewton meter. Okay, so we have now the value of the moment at A, the moment at B, and the moment at C. If we are to do our moment diagram, since our shear diagram is first degree, our moment diagram should be second degree. Okay, so we have here the moment at A, the moment at B, the moment at C, and obviously this is our M max, or our simply the value of our MU. Okay, so I think we are now ready to compute for the value of the C sub B. Okay, so for the value of the C sub B, C sub B is equal to 12.5 of the maximum moment, M max, then divided by 2.5 of our maximum moment, plus 3 times the moment at A, then plus 4 multiplied by the moment at B, plus 3, then the moment at C. Yes, so let us just double check this equation. That is 12.5 of M max, 2.5 of M max, 3 of MA, 4 of MB, then 3 of MC. Okay, so I'll be just substituting this value directly. We have the value of C sub B is equal to, so in our calculator, this is 12.5 of M max. What is our M max? It's 730.52. 730.52. Then to be divided by 2.5 of M max, 730.52, plus 3 times MA, 283.72, plus 4 times MB, that is 500.05. Then plus 3 of MC, 648.72. 0.98. So let's say the value of C sub B is equal to 1.38. So we have now the value of the C sub B. We can now compute for the nominal moment capacity. Okay, so under zone 2, so we can compute for the nominal moment capacity using this equation. So we have the computed value of C sub B, the LR, and the L sub P. Okay, so let us first compute for the plastic moment. We have M sub P is equal to, this is the Fy multiplied by the C sub X. Our Fy is 345 megapascals. That is the same as the newtons per square mm. And the C sub X of our trial section, so it is the plastic section modulus of our trial section, the W21 by 62, is 2,360 times 10 raised to 3. Okay, to be multiplied by 2,360, this is times 10 raised to 3, millimeters raised to 3. So we have the value of our plastic moments now equal to 345 multiplied by 2,360 times 10 raised to 3. So let's say that is equal to 814.2. This is times 10 raised to 6 Newton millimeter. It is 814 million. So 814.2 times 10 raised to 6 Newton millimeter. So all we have to do now is substitute. But again, so let us observe our limit. It should be less than or equal to the value of M sub P. So we are now ready to substitute. This is the value of the M sub N equal to 1.38. Then the quantity M sub P is 814.2. This is times 10 raised to 6 minus M sub P is 814.2 times 10 raised to 6 less 0.7 of Fy 345. So what is the value of our S sub X? Okay, so S sub X is equal to 2080. This is 2080 times 10 raised to 3. Then to be multiplied by the ratio of, that is the LB minus LP, we have 4,300 minus L sub P is equal to 1,906.91. Then to be divided by the LR, this is 5,517.99 less 1,906.91. So I'll just be double checking these values for the value of L sub R and L sub P. So L sub P is 1,906.91, L sub R is 5,517.99. So the condition is it should be less than or equal to the value of our plastic moment, the value of the M sub P. So computing for the value of our nominal moment capacity for our trial section. So let's have this proportion first. The 4,300 minus L sub P 1,906.91 divided by the LR 5517.99, then less LR LP 1906.91. Then to be multiplied by 814.2, this is times 10 raised to 6 minus 0.7 of Fy 345. S of X is 2080. This is times 10 raised to 3. And then this entire value to be less from 814.2 times 10 raised to 6. So minus the answer. Okay, then to be multiplied by our C sub B, 1.38. Then divided by, let's say, if we are to, we can have it that value, or in this form. So we have 838. So we have this as 838.37 times 10 raised to 6. So let's just double check. So 6. 838.37 times 10 raised to 6 ay Newton millimeter. But again, the limit of this value is, it should be less than or equal to m sub p. But this value is obviously greater than 814.2 times 10 raised to 6 Newton mm. So if our m sub n exceeds the value of m sub p, we are to use the value of m sub p, which is equal to 814.2 times 10 times 10 raised to 6 Newton mm. Or if we are to divide this value by 1000 squared, the value of m sub p is now equal to 814.2 kilonewton meter. Okay? So again, we are using the value of m sub p since it exceeds, our m sub n exceeds the value of our m sub p. So this will be our nominal moment capacity, the value of the m sub n. So under LRFD, our nominal moment capacity, or the ultimate moment capacity, or the design moment, design strength, m sub u is equal to the reduction factor multiplied by m sub n. So this is equal to 0.90 of 814. So 814.2 kilonewton meter. So our mu capacity is now equal to, what is 0.9 of 814.2? It is equal to 732.78. 732.78 kilonewton meter. So this is the capacity. So ultimate moment capacity of our section, our trial section, the W21 by 62. If we are to compare this to the actual MU, our actual loading, so what is the ultimate moment capacity based on our loading? Okay, that is slightly lower, 730.52. So this is, our m sub u is 730.52 kilo Newton meter. So this is the actual ultimate moment. So since our capacity is greater than the actual, so we can conclude that the W21 by 62 is adequate. It is, W21 by 62 is adequate, slightly higher than our actual loading. So maybe if we are to encounter this situation, so if we are to increase the factor of safety, maybe we can use a larger section, slightly larger, a section slightly larger than W21 by 62. But again, W21 by 62 is adequate, but we can also recommend, or what is the next section after W21 by 62? Okay, so the next section after W21 by 62 is, it is the W21 by 68. So I'll be just stating here. So we can use W21 by 62, but if we wish to increase the factor of safety, we can use W21 by 68 wide flange. So the next section after W21 by 62. So this will be our solution for this example.